Let's talk about the last of the processes. Well, it's not the last process. Eventually, we'll get to adiabatic. But we'll talk about the case where the temperature is held constant, isothermal, okay? Iso meaning same, temperature. This is a little bit hard to calculate graphically. In fact, it's very difficult to calculate graphically because when we look at this, we know work is the integral of P dV, okay? If we graph pressure versus volume, it's the area underneath that. Well, let me make a substitution here. PV equals nRT. nRT over V is my pressure. So now, if I put that into this equation, work, I have a problem, okay? nRT, this is a constant. It can actually go out front in front of the integral. But now I have the integral of 1 over V dV. Now, if you've taken calculus, you know the integral of 1 over x, or in this case, 1 over V, involves natural log, okay? So when we look at this, again, here is my pressure function. Temperature is held constant. So this curve is due to the fact that as V gets bigger in the denominator, P gets smaller, okay? Well, my isobaric process that I had earlier was easy to calculate because it was just a big rectangle. Now I've got this big rectangle, but it's got this, oops. Now I've got a rectangle. Let me try this one more time. Switch tools. But I've got this big chunk taken out of it. Okay? What does this area down here, let me use green. What does this rectangle look like with this big bite taken out of it? Okay? Well, again, unless we use calculus, we can't really easily find an analytical solution for this. So again, as we integrate this work, we're actually integrating an inverse function. And again, here's the calculus that takes place. Remember, we're dealing with an ideal gas, so we're using this equation right here. We put P as a function of the volume, okay? nRT, these are all constants, right? The number of moles doesn't change as it expands. The gas constant is a constant, so that doesn't change. It's isothermal, so temperature doesn't change. So all these three go out in front. So here is our integral, which is a real classic interval. When we take the integral of 1 over, what we're integrating, we get natural log. Okay, so we integrate this, we get natural log. And although you don't need to know how this is derived, you do need to know that this is the equation for work done by an isothermal system. Okay, so again, a little bit complicated. Understand that this is natural log. If you look at your calculator, sometimes you'll see buttons that'll say LOG. Okay, LOG implies that it's log base 10. Okay, some even have log base 2, but natural log is actually log base E, okay? And E is 2.7, it's a constant, it's 2.7 something, okay? So that's what we're gonna be using. If I graph the pressure at constant temperature, I get what are called isotherms on my graph. Notice at 300 degrees Kelvin, it follows this curve right here. At 500 degrees Kelvin, it's up here. At 700 degrees Kelvin, it's here. 900 degrees Kelvin, it's here. These are, simply just 1/V type plots, okay? And anytime that I follow an isothermal process from an initial point to a final point, let's say I expand at 900 degrees Kelvin, I will follow one of these isotherms, okay? Let's say I start at ½ a meter cubed, and I expand up to 2 meters cubed. Okay, I'm going to follow that isotherm. And the work done will be the area underneath here. So anytime you see that term isotherm, it's just pressure as a function of volume at constant temperature. And again, temperature doesn't change. With an ideal gas, delta T is basically 0. So if it is an ideal gas, in real gases this isn't necessarily true, the internal energy is not changing. And by the first law of thermodynamics, the change in internal energy is equal to Q minus W. So in this particular case, the work done by an isothermal process, these add up to be equal to 0. The work done by an isothermal process is equal to the heat added to the system. Okay? Because there's no change in internal energy, thus there's no change in temperature. And again, to calculate the work done, ideal gas is nRT, natural log of VF over VI.